Aber wir machen jetzt trotzdem weiter mit dem nachfolgenden Referenten, Dr. Douglas Pollock. Dieser hat am Collegio Verbo Divino studiert und seinen Abschluss im industriellen Wirtschaftsingenieurwesen an der Universität von Chile erworben. Sein beruflicher Hintergrund erstreckt sich auf die Bereiche Verwaltung, Handel, Produktion und Geschäftsführung, wobei er an Projekten von der Entwurfs- und Bewertungsphase über die Umsetzung bis hin zur anschließenden Verwaltung beteiligt war. Als Bauingenieur hat sich Douglas in den letzten Jahren eingehend mit dem Klimawandel aus wissenschaftlicher und wirtschaftlicher Sicht beschäftigt.
It's a great pleasure to be in the cradle of classical music, where 200 years ago Beethoven's Ninth Symphony premiere took place. That was the first slide. Now, then comes this one. You already saw it. Now we start. So, let's see first the logics behind the benefits of renewables. This is a game of logics that state that because the fuel cost is zero for renewables since they don't burn fossil fuels, and because the cost of renewables have sharply decreased over the last 15 years, then in conclusion, electricity prices must drop, as well as CO2 emissions. But what happens when there is no cost relationship between statements and conclusions? The entire argument becomes non-valid. Because we also have the facts. For instance, in Europe, when increasing the renewable installed capacity in every country in Europe, the price of electricity has gone up, as well as in Australia and so many other places. But what about the true statements then? We just saw we should be seeing graphs like this one all over the planet. When increasing the renewable fraction in a year, or renewable installed capacity, whatever you want, the price of electricity should go down. This is a real graph coming from the Chilean generation mix over that period. But this graph is bogus, is misleading, is overlapped, because what actually took place, because correlation does not necessarily imply causation, that was a negative correlation, if you want. What really happened was that the Brent oil price, as well as the price of natural gas, came down, and was not because of renewables. Okay, that is about cost. What about CO2 emissions? Well, it seems that, yes, thanks to renewable, CO2 emissions have dropped in Germany, here in Austria, in the United Kingdom, in France, in Italy, in Japan, and so many other places. But again, remember the shark. This is a correlation. It was not thanks to renewable, it was thanks that the electricity generation went down in these countries. So we must solve the problem, because this does not imply that renewables had something to do in this CO2 emissions abatement. Perhaps yes, perhaps no, but we have to prove it, because correlations don't prove nothing. So we will start by building a very simple or basic cost structure. In the beginning, two isolated generation sources, a thermal, a renewable, each one with its technical and cost variables that lead to what we call or know as levelized cost of electricity, which is or stands for the revenue required to build and operate a generator over a certain or given cost recovery period. And here we have the first two figures coming from Lazar 2019. These are two figures when in fact it shows that apparently renewables are cheaper than thermal sources of generation. So what are we doing? Why don't we continue to increase and put more solar panels and more wind turbines around the world? Well, because this is not how a grid works. A grid works in a different way, and we have to analyze it as such, as an integrated system. And what was missing here was nothing less than that. When we increase the renewable generation in the grid, we necessarily must increase a fraction of the thermal generation to back up the natural intermittencies of renewables in order to have stable electricity supply. If not, we simply don't have electricity. And that makes the fuel consumption to increase. And the fuel consumption is given by that formula there, where H is the operating heat rate or the energy necessary to generate 1 megawatt hour of electricity, that multiplied by the unit cost of energy in dollars per mega BTU British thermal units gives you the unit fuel cost of electricity for a thermal source. Now, that goes up when you increase renewables, and that is not accounted for in the levelized cost of electricity. It's assigned to the thermal source, and that is because it's a cost coming from renewables, otherwise it wouldn't exist. And the other costs also, fixed costs also increase because they are distributed in a lower amount of electricity. And why is this? Because when we increase the renewable generation, we must drop the thermal generation, because at every single moment, the sum of both must be equal to the demand in that very moment. We cannot play around with that equality. So then the question is very simple. Why don't we use thermal generation sources instead of renewables? Because of that little thing up there at the left that is called the merit order, by which the generator ensures in every moment the least cost of electricity. And which is that cost of electricity coming from? Mostly is the fuel cost of electricity, the least marginal cost of fuel cost. And for this purpose, renewables cost of fuel is zero. So in having dispatchable electricity, renewables will be always selected over other sources of generation. And this is a very strong assumption, and it operates everywhere around, the merit order. And the other thing that was missing here was, again, it doesn't want to work. Can you give me power? There, the full cost of electricity. Which is that? Is the sum of both costs weighted or multiplied by their respective generation fraction in the grid. And it's not $40, it's not even $56, it's, in this case, in this exercise, 65.4. Why? Because the thermal cost of electricity went up from 56 up to $76 per megawatt hour. So, now, in the absence of renewable, the situation is very simple. We have only one source of generation with a base load, continuous or efficient fraction of generation, and another fraction consisting in a non-base load or inefficient generation for off-peak and peak demand, ups and downs, early in the morning, in the evening, late at night. But in the presence of renewables, we have the dark gray bar there, that is the inefficient thermal generation to back up the renewables, which behave more or less like this, in this range. There will be time when there is enough wind and sun that they will be able to generate at full load capacity, meaning that apparently there will be no need of backup thermal generation. But that would be a mistake, because behind the beautiful green bar there, there's a ghost. And that ghost is called spinning reserve, rotating reserve, or operating at idle speed, which is, I like to use the example of your car stopped in a red light, burning fuel, waiting for a green light, but without moving. This is the same. It's a thermal generation, mostly simple cycle gas turbines, operating at idle, burning fuel without generating electricity, waiting for the wind or the sun to go away. As you can see, the guts of the wind and the sun up there. And when they do go away, then the thermal source will fully replace the renewable generation. It always, and it's all the day, up and down, up and down. In average, that non-base load generation is equal to the renewable generation. And there we come to the first rule of thumb. If grid stability is required or demanded, then for every megawatt of renewable generation capacity, there must be at least 1 megawatt of thermal capacity for backup purposes. Now, seen from the perspective of the generator, as renewable advocates like to show, the cost of renewables remains constant within a range. There's a maximum that will be, for now, we will allow that there's a maximum renewable generation fraction in a grid. For now, let's allow for that. In that range, they remain constant because of the merit order, meaning that when we increase installed capacity, all the generation will be dispatched into the grid. So the unit's costs remain constant. Sorry, how can I back? Yeah, and beyond that limit, that means that any extra generation will exceed the demand, so will necessarily not be generated or lost. So as we continue to increase the installed capacity, then all the cost of the renewable sources of generation will be distributed in a constant generation. But the thermal generation starts increasing from the thermal cost, from the beginning because of the increase in fuel consumption, thus in fuel cost mainly, as well as the other fixed costs. And beyond that limit, there will be no further reduction in thermal generation, making the unit cost to remain constant. But what about if the renewable cost of electricity is much lower than that of a thermal source? It's the same. Because what matters is the full cost of electricity, not the unit cost of electricity of each generation. It's what we pay for, the price or the cost of the grid, the black dashed line there, that always increases, and even worse, it starts increasing from the beginning, from when there were no renewables, and at the same level. Now, there you have the figures of the exercise before. Seen from the grid perspective now, it's the same, but this time the costs are weighted or multiplied by their generation fraction. So the renewable weighted cost starts in zero, increasing, while the thermal weighted cost, oh, surprise, it goes down. And why is this? In this case, you can see K lower than 2. I will explain what is K. In this case, the fuel consumption is not able to cancel or to offset the effect of reducing the thermal generation. That is why it goes slightly down. But again, what matters is the full cost of electricity that always increases. And what is K? Let's go back to the example of your car. Is the fuel consumption of your car driven in the city, including the fuel consumption of your car while waiting in the red light, burning fuel without moving, to the fuel consumption of your same car driven in a highway at a constant speed. That is K, the efficiency factor K. So when K is lower than 2, that is when we mainly, I remark the word mainly because I can't use always. It's impossible, physically impossible. We mainly use combined cycle gas turbines to back up renewables. That's the most efficient way to back up renewables, mainly combined cycle. But what happens when K is greater than 2? That is when we also use simple cycle gas turbines, oil, or even coal, like the case of Australia, for instance. Well, then the thermal cost of electricity slightly goes up, making the full cost of electricity to increase even more. And there you have the same figures, this time weighted by their generation fraction. Now, this is a green trick. We are going to do some magic here. Renewable advocates claim that over the last 15, 18 years, the cost of renewables have sharply declined, which is true. But they're referring to the investment cost, which is not an electricity cost. Notice that it's in units, it's in dollars per unit of power, which is instead a cost of electricity. It's a capital cost in dollars per unit of energy. So they talk about the investment cost. So how do we transform the investment cost into capital cost? We divide 1 unit of the annual payment of the cost of that asset, where R is a capital weight, the weighted capital cost, we divide it by the amount of generation that unit will produce over 1 year. And it's the annual payment divided by the numbers of hours per year by the capacity factor. And the capacity factor is inversely proportional to the, the capital cost, the capital cost is inversely proportional to the capacity factor. And that capacity factor can be 2 to more than 6 times greater than that of a renewable generator. So as you see, it's inversely proportional. Seeing in the graph is perhaps more easy. Let's focus in the red line. If the investment cost of both sources were equal, the same, then the capital cost of a renewable generator would be more than 4 times more expensive than that of a thermal source. So in conclusion, no matter how low the renewable investment cost may drop, its capital cost will still be much higher than that of a thermal source. And that is the trick. They talk about the investment and not the capital cost, which it matters, and it is in fact a cost of electricity. Now let's move to CO2 emissions. This is very interesting because there are 3 ways to reduce CO2 emissions. The first one, like in the case of the 4 nations I just mentioned, by generating less. The second is by replacing coal generation with natural gas, which is mainly the case for the United States. And because the coal generation emits about 2.5 times more CO2 into the atmosphere per megawatt hour than natural gas. And the third one, in theory, by increasing renewables while proportionally reducing fossil fuel-based generation. We will focus on this one, and the analysis for CO2 emissions is exactly the same as the one for fuel consumption, and it's given by that expression there, where we relate CO2 output emissions rate, this time the lowercase e, with the operating heat rate. You may ask me afterwards why 0.06. Now, yes, in fact, if K factor is lower than 2, then the increase in the CO2 output emissions rate is not able to cancel the effect of reducing the thermal generation, making the emissions of the grid to drop. This is the only case that we can get a CO2 emissions abatement by mainly using combined cycle power plants, because if K is greater than 2, which is the case when we also use simple cycle gas turbines, oil, or even coal, then the CO2 output emissions rate increase is able this time to offset or cancel the effect of reducing the thermal generation, making the total CO2 emissions of the grid to increase. And this is insane. This is irrational, because renewables were meant to reduce, not to increase CO2 emissions. Now, here we get to the core of all this. How do we are able in any nation, any grid, any region, whatever you want, able to calculate what is going on in my country? We must discover how to solve that equation. It looks very complicated, but it is not. At the left, you have E is a CO2 output emissions rate, and that is a well-known number in every nation around the world because every country signed the Paris Accord. So they must inform their CO2 emissions as well as their generation. And it's the total emissions of a thermal source divided by its annual generation. So it's a well-known number, but also, let me place myself here because, we can also calculate it as a weighted average of the base load and non-base load generation, weighted by their respective CO2 output emissions rate, respectively base load and non-base load. Omega B at the left, omega N for non-base load at the right. So let's see, because it seems that there are many variables and only one equation, so we have infinite solutions for each one. Let's see. That's a way of to calculate it as a weighted average. We know E. We know the thermal generation. We know omega B, the CO2 baseload output emissions rate. Why is this? Because we know that a combined cycle power plant operating at 95% of full load capacity or 58% efficiency will emit 0.353 tons of CO2 per megawatt hour. We know that figure. What else do we know? We know WRN, or the non-base or inefficient generation to backup renewables, and is equal to the renewable generation. What else do we know? We know the spinning reserve or rotating reserve fraction. What else do we know? Nothing else. So we still have one equation, three variables, no solution for each one, or infinite solution for each one. So what if we are able somehow to know the base load and non-base load generation? Then problem solved for omega in, the non-base load CO2 output emissions rate. And we got that problem solved. Now, two interesting things. Omega n is constant, absolutely constant. So what makes the E at the left to increase is the increase in renewable generation, as you can see. Not because omega n varies, it's because we have an increase in renewable generation. And there we have that omega n is constant for the United States, the entire nation, and we did this exercise for this year, 2022, 2021, 2019, it remains constant always. And why is this? Because of the law of big numbers. Oh, this is a good idea. Perhaps grid operators should require generators to provide generation data separately, baseload and not baseload. Thus, countries would know where they stand in cost and CO2 emissions attributable only to renewables, and what to expect if they continue to increase their penetration in the grid. Today, they are blind, pretending to save the planet from boiling by putting more and more wind farms and solar panels everywhere in every corner. So, let's go now to, the big question. Are we going to have someday 100% of renewable generation around the world? Like this? Looks marvelous. Let's see, perhaps. I will do very, very short high school algebra. Very easy. So don't be afraid. It doesn't work. Can I change the battery? That's it. Yeah. Let's define Q as the installed capacity necessary to generate the annual demand W, or annual generation W. It's the same, always the same. Generation equals demand. That will be equal to the hourly demand D divided by the capacity factor of that ensemble of generators. Now, let's go further and define N as the renewable rated capacity to satisfy the fraction F of that annual generation W is equation 1 multiplied by F. Very simple. Now, here's a condition, which is that condition that will place us in a limit. Is when N, that nameplate capacity, is able to match the hourly demand. It's easy to understand that if we generate more, it will be necessarily lost. Why? Because we cannot inject more electricity into the grid than the one demanded at every single moment. If we try to do that, we blow the grid, because we would be messing around with a variable that by definition must be always constant, which is the electrical frequency. 50 hertz for the United States, 60 for Europe, 60 for South America. That must be always constant. So we replace N equals D in equation 2, and we immediately get the, ladies and gentlemen, I introduce you Columbus egg number 2. The maximum renewable generation fraction in a grid is equal to its capacity factor. We can go further if this stick wants to work. Nope, that's it. We define Q, little q, as the fraction of that nameplate capacity to the hourly demand. So the condition now to be placed in the maximum is that Q must be equal to 1. And here we come to the great genius definition of Christopher Monckton for the end of renewables, which is E, where E is the excess renewable generation capacity that will be equal or will be the difference between its nameplate capacity and the hourly demand. So there you have both equations. You should remember them. And we can explain this also. What can I do here? No, that's it. With a simple graph, let's start by supposing that we have a renewable generation fraction of 0.15 or 15% of the total generation in the grid, with a capacity factor of 25% or 0.25. That means that the renewable facility operating at full load capacity will be able to match at most 60% of the hourly demand. So as business is going so good, we continue to increase. Come on. That we increase now the renewable generation fraction up to 25%, being equal now to its capacity factor. That means that the renewable generation source operating at full load capacity will be able this time to match the hourly demand. And it's very easy to understand that beyond that, no, it doesn't work. Beyond that, any extra generation will be necessarily lost. Whatever you do with it, you may derive it to green hydrogen, green Martians, green batteries, whatever you want, but it won't get into the grid in that moment. Now, let's see what's going on with 15 nations. That's it. Oh, what? Too quickly. That's it. Well, no surprise with Germany, no surprise with Spain. They pass far the limits, meaning that, what does this mean? That with much less installed capacity, they will be able to produce the same amount of renewable generation. That's it. So they're wasting money just for the hell of it. Now, let's see the other 8 nations, where I don't quite trust the figures for China, because these figures come from the Chinese Communist Energy Agency, so I would believe more that China is closer to the United States or India rather to Austria, which, as you can see, is in the limit, exactly in the limit, Q equals 1. So if you allow me, dear friends of Austria, humble advice, stop it now. Don't continue. You will only destabilize your grid, increase the cost of electricity. You will achieve no more CO2 reductions, no more, and no more green generation. You will only spoil your grid and your economy. Oh, and Russia, of course, almost has no renewables. That's it. Oh, the case of the United States. This is very, very interesting because, as I told you, the United States is the only country that divides its generation into baseload and not baseload. So we're able to calculate what's going on in the United States. And for the 2022, I believe, generation, yes, they achieved a 13.6% of renewable generation fraction. Now, in the first row, you have the CO2 output emissions rate, both for natural gas and for all kinds of fuels and technologies, oil, simple cycle, coal, etc. Now, and in the second row, you have the CO2 emissions abatement, which is the amount of CO2 emissions with the current renewable generation fraction minus the CO2 emissions without renewables. In the case of the United States, for that fraction, and using only natural gas as backup, they would have saved or reduced CO2 emissions by 105 million tons of CO2. But it happens that the United States also uses a small fraction, not very large, of oil, simple cycle, as well as coal to back up the marvels, green marvels. So they only were able to reduce CO2 emissions by almost 16 million tons. In percentage, in percentage, that means that only referring to the last column, with respect to the grid, a 0.9% of CO2 emissions reduction. With respect to the country, 0.3. I'm sorry, United States, you're not helping the planet to 0%. The world haven't noticed the gigantic efforts made by the United States after having spent trillions and trillions of dollars to achieve that renewable generation fraction for nothing. There you have it. And this is the last table. This shows in the first row, if we only use natural gas to back up renewables, again for the case of the United States only, then replacing coal generation directly by natural gas generation without renewables will reduce CO2 emissions 24% times more than going from coal generation to renewables, but with the use of only natural gas for backup. You see? Now, as the United States, again, uses all kinds of fuels and technologies to back up these renewables, then going from coal generation directly to natural gas generation will reduce 84% more CO2 than going from coal generation to renewables, but this time with the use of all kinds of fuels. And there you have the figures to calculate the above table, and the conclusion here is very simple. Reducing or reductions in CO2 emissions in some countries have largely been achieved because of replacing coal by gas generation and not thanks to renewables. Yeah, by increasing renewable generation in a grid in terms of costs, the cost of electricity inevitably increases regardless of any improvements from renewables, such as a reduction in their investment cost. The only way for the cost of electricity to decrease is for the fuel cost to drop or going back to coal generation. Now, here, the cost increase analyzed is strongly aggravated by the introduction of costly and damaging market interferences, especially when exceeding the limit for renewables, such as cancellation, curtailment, or constrained orders of generation and capacity payments that have the effect of subsidizing wind and solar generation for non-additional power at the expense of customers. Going too fast. Yeah. Regarding CO2 emissions, although making electricity increasingly expensive, a meager CO2 emissions abatement can be achieved in ideal grids only, thus making renewables economically ineffective for that purpose. But in real-world grids where simple cycle gas turbines and or fuels other than natural gas are also used as backup, CO2 emissions significantly rise, making renewables an irrational solution for the same purpose. The efficient way to reduce CO2 emissions, if needed, which is not, although more expensive, is by replacing coal directly by natural gas generation, getting rid of renewables, which only hinder and inhibits such reductions. And yes, there is a limit for renewables, above which there will be no additional green generation and no further CO2 emissions reduction, if any, before. it will only continue to destabilize the grids and to increase the cost of electricity. And the Western biggest mistake, an asymmetric renewable expansion by decommissioning coal-based capacity without proportionally increasing backup gas-fired generation capacity. Dark clouds on the horizon. I was meaning by this massive blackouts on the horizon. And finally, net zero, an insane utopia trying to become true by imposing extremely expensive green dead weight energies, parasites of any grid and any economy. Western governments, desperate to reduce CO2 emissions with their energy transition policies towards net zero, have put decarbonization before affordability, reliability, and energy security, heading towards an economic breakdown to the loss of energy independence and security of free world nations. By making electricity increasingly expensive, scarce, and unstable, with sweltering climate policies without any measurable impact on climate whatsoever, and even upsurging what was meant to be reduced, CO2, the West is beginning to face the consequences of a colossal lack of rationality and vision by its leaders, who are dangerously compromising access to energy and, in particular, to electricity supply, which this civilization, not the one of Beethoven's, our civilization, is based and entirely depend on. Meanwhile, over the last 7 years, for every unit of coal generation capacity decommissioned in the West, 2.3 units of that same capacity have been built in China and India. Taking the renewable bus to net zero on a highway to hell will drive the West towards a self-inflicted economic collapse. It will only bring devastation and death. Yes, death. Didn't more than 400 people die in Texas 3 years ago during a single 5-day-long renewable blackout? Just imagine that on a global scale. It is no longer speculative that the pointless yet deranged and genocidal climate agreements and agendas translated into national regulations and laws in the name of saving the planet from a non-problem will also bring violent riots, strikes, and coups, for they are already happening, like in Sri Lanka and with farmers across Europe. Yet Western leaders, together with a few non-elected by no one globalitarians, continue to push humanity back to ancient times. Who will finally triumph? Energy abundance and human prosperity, lifting the poorest out of misery, or the net zero extinction agenda? Freedom and democracy, or a global government tyranny? That is something yet to be seen. For now, there is only hope that, in the end, light shall always shine over the darkness of evil. And I wanted to say goodbye, showing you the remarkable resemblance in the Austrian and German landscape with those of Chile. So if you ever go to Chile, you will also feel at home. Thank you very much.